Hi and a very good day to everyone. We are from Lecture 13. We'll be presenting to you about our Apex project, which is Powered Reciprocating Fishing Water Pump System. Without any further, let's dive straight into the video. This project presents a low-cost pump system based on Pascal principle using mechanical torque to move fish and seawater. Designed for small-scale fishermen, it reduces manual effort and minimizes harm to marine life, promoting efficient and sustainable fishing. As for our mission are, first, to develop an affordable, eco-friendly and user-friendly fish pumping system using pressure difference, positive displacement, and mechanical torque to enhance efficiency, safety, and sustainability in small-scale fishing. Secondly, to empower small-scale fishermen with a simple, sustainable pump that reduces labor and protects marine life.
This valve allows water to flow into the system. This valve allows water to flow out of the system. Here is how the valve works. When water flows in, it pushes the ball upwards. The ball then rises until it's stopped by the rod, which holds it in place. This allows water to flow around the ball while preventing it from exiting the system. When water tries to flow back in, the ball is pushed downward. It then seals the cylinder and the access valve, preventing any water from entering, effectively stopping the reverse flow due to the sealed system. Here we have the crank system, which we use the crank slider system. The crank wheel rotates and is connected to the connecting rod. The connecting rod is also linked to the slider rod. As the crank wheel turns, it drives the connecting rod, causing the slider rod to move back and forth similar to a piston. This motion pushes and pulls water in and out of the system. We're using a 12-volt DC 300 RPM geared motor. The geared motor allows us to deliver high torque while maintaining consistent speed. Here, we have 8 1.5-volt batteries connected in series, providing a total of exactly 12 volts, just enough to power the motor. Here's a quick demonstration of the project. As you can see, the piston slider moves back and forth quite smoothly thanks to the lubricant we applied to reduce friction and ensure better motion.
Now, let's quickly review the key expected outcomes for this project, covering performance, mechanical, and fluid delivery. In terms of performance, it should generate sufficient pressure. It should maintain a consistent flow rate and optimize power usage for efficiency. In terms of mechanical, we should produce smooth piston operation. We should produce minimal vibration and noise. We should ensure durability and reliability. And in terms of fluid delivery, we should produce no excessive leakage and produce uninterrupted flow, which is the movement of fish without jams. In our journey to finish making our model, there's likely some challenges that we should confront. Firstly, to find the correct radius of crank wheel. Secondly, to find the correct length of connecting rod. Too short, vertical force will be too much. Third, water flow is not continuous and has slightly pauses because we are only using the single acting valve. And finally, to demonstrate the objects being transferred. What I mean by saying that is, we can't really use the bigger object to demonstrate the movement of fish in the system.
As water flow rate increases, so do pressure, suction force, and flow velocity. This allows the system to safely and efficiently accommodate fish of different sizes. As water flow rate increases, different effects become evident. A low flow rate is ideal for small fish. It's energy efficient but lacks the suction needed for larger species. A moderate flow rate provides the best balance, offering sufficient suction force while keeping fish safety a priority. It's perfect for small to medium-sized fish. However, at a high flow rate, while larger fish can be handled, the intense suction and turbulence could harm smaller species. Therefore, a moderate flow rate between 0.9 to 1.2 meters per second is optimal, providing safe handling, efficient energy use, and making the system ideal for small-scale aquaculture. Compared to traditional systems like vacuum or impeller setups, which are effective but come with high costs, require electricity, and are difficult to maintain, this project presents a simpler, more accessible solution. It offers a low-cost design with manual or low-power operation, and is better suited for small-scale use, especially in rural or resource-limited areas. Despite its advantages, the system has a few limitations. Scalability is a concern, as the setup is currently limited to small operations. Manual calibration demands some technical skill, and regional suitability may vary depending on local environmental conditions. This project introduced a sustainable fishing solution through the development of a powered reciprocating fishing water pump system based on the Pascal's principle. The system focuses on the safety, fish transfer, reduced physical strain, affordability, and adaptability. It addresses key challenges faced by small-scale fishermen and promotes eco-friendly practices by minimizing harm to marine life and reducing reliance on traditional fishing methods. With further improvement and testing, the system can enhance fishing efficiency, support local communities, and contribute to more responsible seafood harvesting.